So there are four sections of these exercises for trajectory data, and we are going to cover the first three. The fourth one is about bicycle trajectories. Since we have not covered the two-dimensional trajectory data, that's in the later part of the chapter, we are not going to discuss this section for now. Whenever we cover that, we'll come back to these exercises. So we'll start with the very first one. Let me know if you can see my screen.
Yes, we can see.
Okay, thanks. So the first one is about these trajectory data, where they say consider the following trajectory data visualizing moving stop and go waves on the California State Route 99. And let me take this and put this in paint so we can draw on top of it. All right, let's see the first questions. First question says determine the traffic density, vehicles per kilometer, traffic flow, vehicles per hour, and speed in the following spatiotemporal sections. So they have provided us the area 10 to 30 seconds and 20 to 80 meters, which is free traffic. And then there's another spatiotemporal region or area, which is for congested traffic. And for these two regions, we need to find traffic density and traffic flow. So let's start with the 10-second to 30 seconds and 20 to 80 meters. So I'm going to also take this part and put that with the trajectory plot. This is what we need to do. So 10 to 30 seconds and 20 and 80 meters. So let's draw a line. I'm going to use the blue color for 10 to 30 seconds. So 10 seconds is somewhere here. Not exact, but this will do. I think it will work. 10 to 30 seconds and 20 to 80 meters. Twenty to 80. So we're essentially looking at this spatiotemporal region, and we need to find traffic density. For density, we have found that it is estimated for a given distance, and which we call as delta x here. So delta x is between 20 to 80. So in this case, it's 60 meters. And we can do that at a particular time, which in this case would be either 30 seconds or at 10 seconds. So we can estimate traffic density at any of these. So let me zoom in and then let's try to count the number of trajectories here. So starting from the bottom here, here's the first one, 2, 3, 4, and this one goes, this is not crossing this boundary, so I would say there are 4 vehicles on this t equals to 30 seconds vertical line, and this is happening within the delta x of 60 meters. But they ask for vehicles per kilometer, so we need to convert this into kilometer. So this should be divided by 1000. If we now estimate that, that would be 4 into 1000 divided by 60. So this is almost 66.7 vehicles per kilometer. For flow, we need to do that at a particular x. So if we take this one, x is equal to 80 meters, and we count the vehicles that are the trajectories that are crossing it, then we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would be 12 vehicles divided by this time interval, which is 30 minus 10, 20. And we want to report this in vehicles per hour. So this is in 20 seconds. We divide it by 60 into 60 to make it in hours. 60 into 60 into 12 divided by 20. That comes out to be 2160 vehicles per hour. So this is the free traffic region, and then the congested region is somewhere here. But to save time, let's look at the result of the free traffic first. The results are 671. All right, so here it says 11 vehicles divided by 20 seconds. I counted 12 vehicles divided by 20 seconds, so that's almost the same, which comes out to be 1980 vehicles. In our case, that was 2160, so it's pretty close. And for density, it's 3 vehicles divided by 60 meters. I counted 4 vehicles divided by 60 meters. So again, similar result for the free traffic. It also estimates the speed. Let's see. Yes, it also asks for speed in the following spatial temporal sections. If you want to estimate speed, one way to do that is to look at the gradient of one of the trajectories. So for example, if we want to look at this one, or let's select this one. So this one has a trace on top of it. This is the time. So since this is 20 seconds, this may be about 22 seconds. And this one is very close to 30. Let's say this is 28 seconds. So we need 2 coordinates. For this point, let me use a different color here. For this point and for this point, we need the x and y coordinates. So the x coordinate here is 22 seconds, and the y coordinate is 20 meters. 20 comma 20, 22 comma 20. And here the x coordinate is about 28 seconds, and the y coordinate is 80 meters. Now to estimate the slope, we do y2 minus y1 divided by x2 minus x1. So y2 in this case is 80 minus y1 is 20. and x2 is 28 minus x1 is 22. This comes out to be 60 and 6, so that would be 10 meters per second. So this is just one trajectory that we selected, and then we looked at its Cartesian coordinates and estimated the gradient. Since this is distance over time, this will give us the speed. So looking at that, they also do 60 meters divided by 5 seconds. And we did 60 meters divided by 6 seconds, so not very far off. Gives us about 43 kilometers per hour. And we can also use the hydrodynamic relationship, which we learned about in the previous two chapters. So that would be flow divided by density. So if we plug in these values, that comes out to be about 40 kilometers per hour, which is similar to the gradient-based speed. Here it says the discrepancy is tolerable in view of the reading accuracy. And then they also have estimated for congested traffic the same items, flow, density, and speed. So to save time, we are not going to do that. Let's look at the next question.
Before proceeding,
Yep.
like when we have done for the free region, could you please go to the paint? So, like we took the number of cars at t equals to 30, but if we are going to read at t equals to 10,
Yeah.
because the distance is there, I think we're going to read only 3 cars, isn't it the case?
Yeah, the number of cars could be different. So let's do the count here. So in this case, this is one vehicle that's passing. Here we have two, and then here we have three. So here I counted four vehicles, and then here we are counting three. So the way that they have done this in the chapter was to take an average. So that would be 3.5 in this case. And if you round up, that would still become like four vehicles. So there could be some discrepancy between counting it here or here.
But it should be the same, yes? Assuming that the number of flow of constant cars are constant.
Not necessarily, it can be different because maybe there is a vehicle that entered in this region, but then changed the lane. So this plot that we're looking at, this is, I believe, for the second lane. Stop and go waves. Highway lane 2. Yeah. So this is for just one lane. So if the vehicle entered in this region, although in this case it did not happen, but it may happen that the vehicle that entered may also leave this lane. And if that is the case, the count will be different. In this case, although there are no vehicles leaving this lane, the count is different because it depends on what was happening upstream of this region. So maybe some of the vehicles entered this region later in time and their speeds were different compared to what was happening at t is equal to 30 seconds. You can see, for example, there is this clear gap between these trajectories, which means that there was no vehicle that entered here, which also means that the number of vehicles that leave at t is equal to 30 seconds can be different than the number of vehicles who enter at t is equal to 10 seconds. So it depends on what their speed was and what was the traffic flow at the time.
But for example, for a practical purpose, I know it's going to be very tiresome, but if we can count like the number of the densities for all the region, like
Yeah.
an average would not be representative than taking one extreme.
Yeah, as we discussed in the previous chapter, It's a very good point because looking at only this region, we can clearly see that almost all the vehicles have the same gradient, which means that this is a stationary region, stationary in terms of statistics, which means that their speed distribution is not changing. The speeds are more or less the same. But compare this region to this region. In this region, we can clearly see that, for example, some vehicles are completely stopped, right? And some vehicles are slowed compared to these vehicles. The slope of these trajectories is much higher than the slope of these trajectories. So when we compare between different regions, their speeds, their traffic flow and density can be significantly different. So whenever we are taking an average, we should make sure that the stationarity is upholding, which means that they are similar. So this region that the question asked about, this is between 10 to 30 seconds and 20 to 80 meters. This is more or less a similar distribution of vehicles. And so that's why when we count here, we counted three, here we counted four. There isn't a lot of difference between the traffic density. Similarly, if I count at the top for estimating traffic flow, or at the bottom, or at any point, at any X point, we'll see they're more or less the same. There won't be much difference because the region itself is stationary in terms of, and we say statistically. So they're not changing a lot. Did that answer your
I'm sorry.
question?
I'm sorry. Yes, yes, yes. I'm sorry. I'm asking too many questions.
No, no, that's the
So
point of the book club.
yeah. So from 50 to 60, I'm sure if you're going to draw, it's not going to be the same as the free flow region. So are we going to count the number of vehicles who are not who are moving and not like because for example, if we draw the region, there are
Yeah,
cars that have been like in stationary, and there are cars that are approaching within that region of 50 to 60.
yeah. So if I just put that once again, we can actually do the calculation for the second part, and I think that would show us that difference. Let me grab the plot first. Okay. So in the second part of the question, we do need,
50 to 60 and 40 to 100.
yeah, 50 to 60 would be, so we're here, that's 50. And you said 50 to 60 seconds?
Yes.
It's 50 to 70
Yes.
seconds and
70.
2200.
Oh, okay.
Um,
Yes, yes. Sorry.
all right, 70 and 2200. 70 will be
20
here,
and 100.
100 is here. And so this is a region. So if we count for traffic density, and let's do that with a different color. We count for traffic density. So here's one, and this one is also crossing the yeah,
But
I
I
think
think
so.
it was changing lanes. We cannot count that.
Yeah, we can, it's still crossing that point, right? So in this case, if we don't count this one, then it's three, otherwise it's four. On this side, we have one, two, three, four, five, 6, 7. Yeah. So 7 here and 3 here without counting the lane changing vehicle. So here we clearly see the difference because when they entered, we can see upstream they had higher speeds. But when they entered, they slowed down, and then only 3 vehicles left at t equal to 70 seconds. So that means that there is a significant change in their speeds here. And so based on that, if we estimate the density, that would show us different numbers. So here for free traffic, the density was 60 vehicles per kilometers. For congested, it's 1,000. I counted 7, they counted 6. Yeah, so similarly, flow is different. The flow is smaller compared to the free traffic, and the speed is also smaller. It was 43 kilometers per hour, it's now 7.2 kilometers per hour. Okay, so that was the first question. Second one is find the propagation velocity of the stop and go wave. Is it traveling with or against the direction of traffic flow? For the propagation velocity, we need to look at where the stop and go wave is. So let's try to do that. Let's get rid of these lines first. The stop and go wave is where the vehicles start to slow down. So this is one line that represents that. And then the second line is here. So these two lines are the boundaries of the stop and go waves because before the first line here, upstream, the speeds were higher, then they slowed down, and then their speeds increased again. So these are the two boundaries. If we estimate the slope of any one of these two lines, that will tell us what is the propagation speed. Because again, this is distance on y-axis and time on x-axis. So if we estimate, for example, the slope of this line, let's do that here. This is about 160 meters. That will be, let's see, what's the x here? X is on
History.
55, so roughly 55 and 160. And this point is where we have uh, almost 75, and x is 0.
Mhm.
Sorry, the y is 0. So now again, we do y2 minus y1 and x2 minus x1. Y2 in this case is 160 minus 0 divided
And
70, sorry, 55. Uh, actually,
minus 100.
y2, this is, this should be y1, x1. So in that case, y2 was 0. So I should say 0 minus 60. And here I should say 75 minus 55. So that comes out to be minus 160 divided by 20. So minus 8. This is in meters per second. That's the propagation speed. And this is the direction of travel. The vehicles are traveling from here to here. That's the direction of travel. And based on that, this is happening against the direction of travel. So that's why we have a negative speed. Let's look at the solution. So it says a stop and go wave can be identified by the spatiotemporal region with nearly horizontal trajectories. First, we observe that in the diagram, the gradient of the essentially parallel upstream and downstream wave boundaries are negative, which we also found. That is, the wave propagates against the direction of traffic. To determine the propagation velocity, we estimate from the diagram. So they are taking 140 meters instead of 160 that I did here. So they actually took this value, didn't consider this trajectory, and divided by 60 minus 33. If we take these values, 140 here, so here, this is not drawing it correctly, but it's roughly 60.
I think they've used the lower green bar than the other.
Yeah, I agree. So that's the 60 part, and then this is, according to them, 33 seconds. Yeah, so we can take one or the other boundary here. And based on that, we get, so here this is minus 8 meters per second. And if we look at this one, this is minus 5.2 meters per second. So lower than what we estimated, but the methodology is the same. Okay, going back to the questions. Question number 3, estimate the travel time increase incurred by the vehicle that is at location x equals to 0 meters at time t is equal to 50 seconds due to the stop and go wave. Okay, so let's get rid of these annotations first. The easiest is to just delete this and then paste the plot again. And now we want to look at t equals 50 seconds at x equals to 0, which comes out to be like this. So we are looking at this trajectory. And so it were to continue and it did not change lane, it will continue like this. So the question is, what is the travel time increase? Again, estimate the travel time increase incurred by the vehicle that is at location x equals to 0 at time t is equal to 50 due to stop and go wave. If the vehicle never slowed down like it did in this region, then the trajectory would continue like this. If I draw a line, and let's try a different color here, and I use the same slope and I extrapolate it to this point, then essentially we're looking for the time difference between these 2 points. If it were moving with the free speed it had before slowing down, that's the trajectory that we would have gotten. So this time is, let's take perpendicular here. It's maybe 60,
63,
65, 64. Okay, so 64 seconds. And this one is, so another line, 82, 83.
Yes.
Okay, so if it is 83, then it's 83 minus 64. So that would be the time that it has lost. So that's the increase in the travel time. So about 21 seconds. Let's say what the solution says. Okay. Okay, travel time increased without being obstructed by the traffic wave. The considered vehicle entering at t equals to 50 seconds into the investigated road section, x equals 0, would leave the section at x equals L equals 200 meters after about 16 seconds. This can be deduced either by linearly extrapolating the first seconds of the trajectory or by the quotient L over V free. The actual vehicle leaves the investigated section at t equals to 86. So I estimated that to be 83. They have 16 seconds. I have about 20 seconds. Here they say thus the delay imposed by this traffic wave on the vehicle is 20 seconds. So, yeah, so it's roughly the same. 20 seconds, 21 seconds. Okay, next question. Estimate the average lane changing rate, lane changes per kilometer and per hour in the spatiotemporal area covered by the data set. Assume six trajectory beginnings or endings within 0 to 80 seconds and 0 to 140 meters. Okay, so in this case, we have, so they're saying to consider only this region 0 to 80, 0 to 140. 0 to 80, that's here, and 0 to 140, that's here. So all of this region. They have already given us the number of lane changes. They say assume six trajectory beginnings or endings within this region. So if there are six lane changes and we want to estimate the lane changing rate, we divide by the spatiotemporal region. To estimate the spatiotemporal region or the area, we just simply multiply uh, these coordinates. So we have 80 by 140. So if we say six lane changes divided by 80 by 140, so this is the 80 seconds from 0 to 80 seconds and from 0 to 140 meters, that will give us the number of the rate of lane change. So if we estimate that, 6 divided by 80, then divided by 140, 0.0005 per second meters. That's the lane change rate. Yeah, so 6 divided by 80 and 140 changes per meter seconds. And if we convert it into kilometer hour, that would be 1900 lane changes per the area of 1 kilometer into 1 hour. Okay, going back to the questions. Any questions before we go to the next point?
No.
All right. Trajectory data of obstructed traffic. Consider the trajectory data of city traffic shown in the diagram below. What situation is shown? What does the horizontal bar beginning at x equals to t equals to 0 mean? So I remember that this was discussed in the chapter also. and we already know that the situation is that there is a
Yeah.
traffic light at this location. So this black bar is representing the traffic light. What does the horizontal bar beginning at? Yeah, so I think that answers the question. So upstream of this traffic light, we have vehicles that are traveling at their free speed. We can see that the gradient of these trajectories is higher compared to these trajectories that are completely stopped. So their gradient is similar here, but when they approach the traffic light, they completely stop. And then at this point, they start to accelerate again, and then they maintain their free speed again. So these red points are representing the start of the deceleration, and the blue points are representing the end of the acceleration after they start to accelerate. Question number two, determine the traffic demand, that is the inflow for t less than or equal to 20 seconds. Okay, let's take this plot. So the question is about inflow for t less than or equal to 20 seconds. So t less than or equal to 20 seconds. 20 seconds is right here. Let's use a different color. So 20 seconds is right here. And we are looking at, we want to estimate the flow. The flow can be estimated at a given x location. If we estimate the flow at x equals minus 80 meters, then we count the number of vehicles that are crossing this particular location. In this case, let's count this as the first one, two, three, 4, 5, 6, 7, 8, 9, 10, and 11. That would be 11 vehicles that have crossed over 40 seconds. If you want to convert it into hours, that would be 40 divided by 60 into 60. So if we do that, 60 into 60 into 11 divided by 40, that gives us 990 vehicles per hour. Let's see what the solution says. Okay, so let's first look at the solution to the first one. The data shows a queue at a traffic light. The horizontal bar marks the position of the traffic light and the duration of the red light phase. Yeah, duration of the red light phase is an important point. Okay, question two. Flow Q in is 5 trajectories per 20 seconds is 0.25 vehicles per second. That would be 900 vehicles per hour. Okay, so they're not counting less than zero here. We did count that. If we don't count it, then it's one, two, three, four, five, and six. So six vehicles. So in this case, they counted 5 trajectories per 20 seconds. So for these 20 seconds, they're counting five. So I don't know why they didn't consider this part, although in the question it says t less than or equal to 20 seconds. So that should include this part. But roughly it's the same. We have 990 vehicles per hour as per our calculations, and their calculations say 900 vehicles per hour. Okay, let's Go to this third question. Determine the density and speed in the free traffic regime upstream of the obstacle. So we want density and the speed, and that is in free traffic only before the obstacle. Okay, so the obstacle is the black bar here. So essentially, we are looking for the speed of one of these trajectories because they have the same gradients. So let's take this one. So we have this point and we have this. If I draw a line here, this is almost 10 seconds. I would say here is 10, comma, this is 40 to 40, that would be 20. So this is 100. So that's x2 and y2. And in this case, we have almost minus 10 seconds. Then this will be minus 10, comma, minus 80. So again, y2 minus y1 divided by x2 minus x1. Y2 is this 100 minus 80 divided by n minus 10. That's 180, and this is 20. So that comes out to be 9 meters per second. That would be the speed. And if we also want to estimate the density, we do that at a particular time. So let's take this line that is t equals to minus 20 seconds. At this point, we count this vehicle, 2, 3, 4. So that would be 4 vehicles divided by um, this is 180 meters. Okay, so 9 meters per second and 4 divided by 180 for density. Let's see the solution. Okay, so following the trajectory which starts at x equals to minus 80, t equals to minus 16, and which ends at this point, we get the speed of 10 meters per second. So we estimated that to be 9 meters per second, so pretty close. Density is read off the diagram as one trajectory per 40 meters, or is calculated using rho equals to q over v. So one trajectory per 40 meters, 1 divided by 40. And what we have here is 4 divided by 80. Okay, pretty close. 4 divided by 180 and 1 divided by 40. That was 1 divided by 40 is 0.025, and 4 divided by 180 is 0.022. So very close. Okay, let's go to question number 4. Any questions?
The discrepancy came because they only count For example, at minus 20, you can see that the uh, cars passing started at minus 80 and stopped at 40. So we should not count 100. It's only going to be the distance is going to be from minus 80 to 40, which is going to be 120.
You mean this part?
The left side, yes, at minus 20, t equals to minus 20.
Yeah,
You can see that one car is coming up every 40 seconds. No,
yeah,
every 40
40
meters.
meters. Yeah,
But we in our counting we included 100-meter distance where there is no car in the coming on the left on t minus 20. So that's why they took that side, yielding 120 or four in every, like one car in every 40 meters.
yeah, I agree. Um, yeah, so I think that difference will always be there because this is manually counting. But you are correct that that's how they have estimated it for every 40 meters. So that is pretty clear from the plot as well. Yeah, good point. But I was also, based on the point that you raised, I was also thinking about scaling up this kind of analysis. So right now, the questions that we are solving, these are smaller scale questions. We are only looking at one part of the trajectories, but there are obviously multiple lanes, and we also may be looking at a very long stretch of the road and for hours at a time. And so in that case, scaling up these calculations is, I think it requires some kind of automation rather than just manually estimating
Yes.
density and flow. But on the top of it, I also wonder what is the application of looking at density and flow at different points. We know that in general, the applications would be understanding what is happening to the traffic flow, but it would have been nice if the chapter discussed how, once we get these calculations, how those are applied. Maybe it is discussed later in the chapters. Okay, so question 4 is about determine the density within the traffic jam. So within the traffic jam, we have this area. If we consider within the traffic jam, if we consider the 20-second point, which is almost in the middle of this congested area, and we look at this line that t equals to 20 seconds, we can count. If we count this vehicle, second vehicle that is crossing, and then these are stopped, the one, two, three, four, five, six, seven vehicles over 80 meters. That's the solution here, 673. Density in the congested area is 8 horizontal trajectories per 40 meters. So they've only considered 40 meters. They haven't considered the 80 meters that I did, and they're saying there are eight horizontal trajectories. One, two, three, four, five, six. Within 40 meters, here I only count six. They say eight.
How about we take like t equals to 40 seconds?
Uh, yeah, we can do that. equals 40 seconds. So here, let's count these. We have one, two, three, four, five, six, seven, and eight. Correct. So we get eight trajectories within the 40 meters. Good point. But I wonder why they don't consider this part by just the 40 meters. Why not this section as well?
I think maybe because like most of the cars were like not in a congestion state. Below cars below like minus 40 are almost approaching, and the
Yeah,
other cars were stopped for some 10 seconds or something.
agree. Yeah, yeah. So they define the congested region as 0 to negative 40. Okay, let's go to questions. So we have already looked at question number 4. Number 5 is determine the outflow after the obstacle disappears. Also find the density and speed in the outflow regime after the initial acceleration, the end of which is marked by smaller blue dots. So we need outflow. Okay, we also need density and speed in the outflow regime after the initial accelerations. So after the initial acceleration means after these blue dots. So we know that these trajectories have the same gradient as these trajectories. I don't think there is a difference. I think roughly their speed would also be about 9 to 10 meters per second. And if we want to get the density, we can do that here at t equals to 80. And if we count these, we get this one, two, three, four, five, six, seven, eight. So that would be 80 vehicles, sorry, 8 vehicles per 180 meters. I would say that's the density. So let's see. And okay, they also asked about flow. So flow can be obtained at any X location. So we can maybe do that here. One, two, three, four, five, six, seven, 8, 9, 10, 11. That would be 12 vehicles divided by um, the time that we are looking at. So the time is uh,
80
maybe
minutes.
starting here. So that's like 50 to 80 within 30 seconds. Let's see. So this was question number 5. Solutions. Outflow after the red light turns green. The best way is to count the number of lines within a 20-second interval above the blue dots. Okay, they did that for 20-second interval instead of 30 seconds, marking the end of the acceleration phase, giving 10 lines per 20 seconds, and thus the flow will be 0.5 vehicles per second. So they did 10 over 20, and we did 12 over 30. Okay, so that comes out to be 1800 vehicles per hour. The speed is the same as in the free traffic, so that's 36 kilometers per hour or 10 meters per second, which is correct. We obtained that to be 9 meters per second previously. The density is obtained again by counting trajectories, 2 lines per 40 meters, or via the hydrodynamic relation. So it's 2 divided by 40. In our case, it's 8 divided by 180, which is not different, I guess. Okay, next. Um, so question number 6, determine the propagation speed of the transitions free traffic to jam and jam to free traffic. Propagation speed of the transitions. So propagation speed is, let's put the plot again. So in this case, I think propagation is happening like this. And so if we estimate the gradient of this line, that will tell us what is happening when we are going from free traffic to congestion. So these points, as I previously mentioned, these points represent the start of the deceleration. So they are arriving and they are moving at a fixed speed, a uniform speed. At this point, they start decelerating and then they completely stop. And then here, they start to accelerate. And then here, they are moving at a uniform speed. So this is the end of acceleration. This is the start of deceleration. So we have this line that goes from free traffic to jam, and then we have the second line that represents the jam to free traffic. So if we have the gradient of this line and the gradient of this line, that will give us the propagation speed. You can also see that this is against the direction of traffic. So this is going to be negative speed. So now because we are out of time, let's quickly look at the solutions for these three, and we'll leave trajectories of city traffic for the next time. So actually, let's just look at the solution to question number 6, and then we'll handle the other two later. So 673. Question number